Welcome to lecture 56. We are discussing design of transonic compressor. So this design, that's what is mainly been focusing for the pressure ratio of the order of 1.63. Mass flow rate, that's what is fixed with 38.69 kg per second, and we have our design constraints. For that, in initial stage we have assumed certain axial velocity numbers, say peripheral speed. Based on that, we have done our calculation for entry, we have done our calculation for say exit of the stage. In between the stage, that means at the exit of my rotor and at the entry of stator, we have done the calculation for the radius, and at mid station we started doing the calculation for say different parameters. So when we are discussing about say design at the mid station, we have assumed our pressure ratio to be expected pressure ratio at the mid station, that is 75% of span. We have done our calculation for all flow parameters, flow angles, and in order to have say calculation for the number of blades, we have assumed our diffusion factor to be 0.32 at mid station, and that's what was helping us for the calculation for say solidity. Based on the aspect ratio, we have done our calculation for the chord, and let's move towards the next calculation. So as we know, once we have done our calculation for the mid station, we are interested in what is happening at the hub station, what is happening at the tip station. So let's move with the calculation at the hub station. Now here in this case, we have considered our fundamental design approach. That means we need to assume certain pressure rise expected near the hub. Okay, so say for the sake of understanding, say for simplicity, we are assuming our pressure ratio expected at the hub to be 1.4. That means that's what is giving me my total pressure rise expected to be 40530 Pascal. So do not get confused from where this number, that's what is coming. That's what is approximately we are assuming our pressure ratio of 1.4. Okay, if that's what is the case, at the hub station we can do our calculation for say total pressure rise. So here in this case, at the entry my pressure P01, that's what is known to us. This is what is say my total pressure what we are expecting, that's what is 40530. We are assuming our efficiency to be 93%. That's what is giving me my delta T0 at the hub to be 32.33 Kelvin. Now this is what is very much helpful for us in order to do the calculation for different velocity components. So what we will be doing, say in line to what we have done at the mid station, we will be assuming our aerodynamic work and thermodynamic work to be same at the hub station. If we are putting that as a case, my CW1, as we have discussed, it is axial entry. That's the reason why CW1, that's what is equal to 0. And if we are putting these numbers, it says Cp delta T0 divided by lambda into U at exit. That's what is giving say work component, it is as a 164.52 meter per second. Now once at exit station, this is what is known to us, it will make our calculation easy. So let's move with what velocity triangle we will be having. So this is what is representing my velocity triangle at the entry of the rotor. This is what is a velocity triangle at the exit of the rotor. So based on our understanding, we are having our axial entry, that means alpha 1, that's what is equal to 0. Beta 1 we can calculate based on U by Ca, that's what is coming 33.68 degree. Same way beta 2, that is at the exit station, we can do calculation, that's what is coming 9.35 degree. Now here in this case, if this is the case, we can have our delta beta, that's what is coming 24.33 degree. Okay, so with this delta beta, we will be moving forward with say calculation of alpha 2. we will be calculating what will be our relative velocities. Okay. So, based on velocity triangle, we can say tan alpha 2, that is what is CW2 divided by CA, and this is what is coming as a 36.17 degree. Now, in order to calculate our degree of reaction, as we have discussed, we will be taking say peripheral speed to be average peripheral speed. So, at hub, at the entry we have UH1, at the exit we have UH2. If we are putting that as average, it is coming 175.74 meter per second, and if we are putting that in the equation for degree of reaction, the degree of reaction at the hub, that is what is coming 0.53. Okay. Now, in order to do the calculation for relative velocity components based on velocity triangle, we can say cos component of beta 1, that is what is given by Ca by Vh or V1, and that is what is giving me relative velocity component at the hub. At the entry, it is 270.32 meter per second. Similarly, at the exit, we can do this calculation. It says 228.03 meter per second. We can say the number, we need to be careful, we need to keep on eye with say V1 and V2. You can say this is what is coming as say 228.03, that is what is indicating the diffusion, that is what is happening. And that is why if we are calculating our de-Holler's factor, that is what is coming 0.84. So, this is what is in the range of what we are deciding with 0.72. Now, in order to do the calculation for say our diffusion factor at the hub station, we need to have some parameters. So, since we have already assumed our diffusion factor at the mid station to be 0.32, and based on that we have done our calculation for number of blades. So, for the same number of blade, we can calculate what will be my pitch, okay, and that pitch is coming 0.025 meter. And based on that pitch and chord, say here we are assuming our chord to be constant. Okay. So, there are many design where people they are assuming this chord to be different. Okay. So, such kind of design, that is what we will be discussing as and when required. So, at this moment we are assuming our chord to be constant from hub to tip, and that is the reason why it is giving me solidity as 3.665. Once the solidity is known to us, we can do our calculation for diffusion factor at the hub, and that is what is coming 0.21. Okay. Now, in order to understand, like in order to do the calculation at the tip, so here as we know, this is what is our fundamental design approach, in which we need to assume our delta P0 distribution. So, at the tip we are assuming, suppose say our pressure ratio to be say 1.66 near the tip region, and that is what is giving say my pressure rise expected to be 67,000 Pascal. Okay. If that is what is the case, we can do our calculation of say my delta T0 at the tip station, and this is what is coming 50.01 Kelvin. Okay. Now, in line to what all calculation we have done at mid station and at the hub, we can do our calculation by comparing aerodynamic and thermodynamic work. So, here in this case as CW, that is what is at tip station, CW2 at the tip station, that is what we can calculate by comparing our aerodynamic and thermodynamic work. So, if we will be putting that number, it says my world component at tip at the exit, that is what is coming as say 128.46 meter per second. Okay. Now, based on this, we can do our calculation for different velocity components near the tip region. So, alpha 1, that is what we are assuming to be 0, we are considering axial entry throughout the span. Okay. And based on our velocity triangle, we can calculate what will be our beta 1 at the tip and what will be by beta 2 at the tip. If we are considering beta 1 at the tip, it is coming 60.59 degree, and beta at the tip that's what is at the exit, it is coming 50.27 degree. Okay. Now this is what will be giving us our delta beta to be in the range of say 10 degree. So this is what is 10.32 degree, and based on that we can make our blades. Okay. Here in this case, from the exit velocity triangle we can do our calculation for alpha 2. This alpha 2, that's what is will be helpful for us in order to do calculation for the stator. Okay. Now based on all this calculation, we are looking for say degree of reaction at the tip station. Again we will be doing our peripheral speed averaging, and this average value, that's what is coming 399.22 meter per second, and that's what will be giving degree of reaction to be 0.84. Okay. Now all these numbers what we are discussing in sense of degree of reaction, you must realize what is the meaning of this degree of reaction. That's what is varying all the way from hub to tip. Okay. Now based on what all calculation we have done for our blade angle, relative inflow blade angle, relative outlet angle, we can calculate what will be our relative velocity at the entry, what will be our relative velocity at the exit, and based on that we can do our calculation for de Euler's factor. So from velocity triangle we can write down our relative velocity at the entry, that's what is Ca by cos beta 1, and that's what is coming 458.26 meter per second. You can see the range if we compare what is happening at the hub and what is happening at the tip. Same way at the exit we can do calculation. It says this is what is coming as a 352.05 meter per second. Based on this relative velocity we can do calculation for our de Euler's factor, and that's what is coming 0.77. It says that need to be more than 0.72. So we can say this is what is coming in line to what we are expecting. Okay. Now say at the tip we have already assumed with our number of blades, that's what it say 29. So we can do our calculation for the solidity at the tip station. Here let me say its chord, that's what we are assuming to be constant, that's what is coming 0.09 meter, and we can do calculation for the solidity. This is what is coming 1.61. So based on that we can do our calculation for the diffusion factor. For diffusion factor at the tip, this is what is coming as a 0.32. Okay. Now after doing all this calculation, as we know, we can make our Excel sheet program. That's what will be helpful for us in order to cross check with what all calculation we have done at hub station, mid station, and at the tip station. Now here you can see this is what is giving us the variation of delta P0 all the way at the hub, mid station, and at the tip station. Now you can divide, say from hub to span, you can divide into some number of station. Same way you can divide from say 75% span to tip span as say some number of stations. Okay, and based on your design program you can do all your calculation for. But here in this case we need to assume this delta P0. So this delta P0 assumption, that's what need to be very careful with catch on eye for what is my delta beta. It should have particular train. This is what all we have discussed when we have done design for our subsonic compressor. So in line to that only we need to assume our delta P0 in such a way that delta beta will be coming in line. Second observed parameter, that's what is in sense of my de Euler's factor. Same way we can catch on eye with say diffusion factor. Okay, even we can check with our camber angle variation. So this is what is a calculation we can say at 3 different stations. Now let me put the point here. So after doing this design, we will be looking for the design for the stator. So for stator design at the mid station, what we are assuming is a what is my absolute velocity at the exit of rotor, that's what is equal to absolute velocity at the entry of my stator. Okay, and here in this case my alpha 2, that's what is equal to alpha 3. This what we have calculated is say 31.98 degree. Now at the exit we are expecting the exit to be say axial 1, and this is what is say in line to what we say assuming alpha 4, that's what is equal to 0. Now here if we look at what is happening in sense of our axial velocity at the exit of the rotor, this is what is coming in the range of subsonic flow. Okay, so that's what is giving us indication that our stator, that will be subsonic stator. So based on design, so this is what all we have discussed when we were discussing about the transonic compressor. So there are many compressors in which you will be having your absolute velocity coming out from the rotor, that's what is on higher side, and under that condition you need to go with your stator to be supersonic stator. Okay, so here in this case these numbers, that's what is coming to be in slightly lower range, in subsonic range or high subsonic range, we can safely go with say subsonic kind of stator, and that's the reason why if you look at this aerofoil, that's what is say subsonic aerofoil, we can say we can go with say C4 kind of aerofoil for this. Okay, initially you can go with C4 aerofoil, later on as per your requirement you can modify the shape, you can morph your aerofoil as per the expectation. Here in this case my delta alpha, that's what is coming to be say 31.98. Now this is what is a kind of configuration we are discussing at this moment. Now next step, that's what is for the design of stator. Here also we are looking for what will be the height and what need to be the chord. Even we need to have assumption, or we need to have say number of blades for the stator. So for the sake of understanding, here also let's assume say aspect ratio to be 1.4. Okay, this 1.4, that's what is coming with certain assumption in order to catch on eye for the chord of our stator. Okay, so here we have assumed this aspect ratio to be 1.4, and as we have discussed, we need to calculate our height based on entry height and exit height, and this is what is my average height. So this is what is in line to what we have done for our say rotor. Okay, same way you can calculate your average height for the stator, and this is what is coming 0.11 meter. Now this chord calculation, we can say this is what is coming as a 0.08 meter. So we can say this is what is in line to what we are expecting. Suppose again we need to be very careful, this number, if this is what is coming to be lower, under that condition maybe you need to modify your assumption for aspect ratio. Okay, so certain assumptions when we are making, we need to be very careful in that aspects. Okay, now once this is what is known to us, next parameter, that's what will be coming is for the selection of say number of blades for the stator. Okay, there are different approaches for say assuming say number of blades for the stator. Here in this case what we will be saying, in order to limit our diffusion factor, say we have assumed our diffusion factor for the rotor, diffusion factor for the stator also can be assumed, but do not go into the detail. We will be doing say assumption for say solidity. Let's assume the solidity to be 2. You may be having questions, sir, why 2? You can go with a lower number, you can go even with higher number. Okay, why we are assuming this solidity to be 2? Let's see. So here based on solidity to be 2, we can do our calculation for say number of blades, and this number of blades, that's what is coming say 36. Okay, so many times as we have discussed earlier, mechanical engineers, that's what they will be putting, they will be insisting to have say maybe less number of blades. Again, this less number of blade and more number of blade, it is a hot discussion for the design. Okay, when we are looking for say design in which we are expecting our say weight of the engine to be lower, it is but obvious it says you go with say lower number of blade both for rotor and stator. But when we say we are assuming our number of blades to be say lower, it may be possible that it will not give what performance we are expecting, because my flow passage will be it's a diffusing passage, and when we are having less number of blades, it may be possible that we will be having say special kind of configuration where we will be having say diffusion action will be lower. There are many chances in which you will be having the flow separation, that's what will be happening towards the trailing edge. Okay, so those all things, that's what will be coming when we will be doing the detailed design. At this moment, this is what we are doing as a preliminary design. So we are taking our number of stators to be 36. Now once this is what is done, we can say we are calculating our say M factor, that's what is my slope factor. So my slope factor, that's what we are calculating based on alpha. So this is what is representing my cascade. Okay, so we will be taking this as a parameter. Here in this case, when we are calculating our camber angle, again at the mid station, even for stator, we are assuming our incidence angle to be 0. Okay, so if I am taking that to be 0, at mid station we can do our calculation for camber angle, and that's what is coming 45 degree. Now we can do our calculation based on Carter's relation for the deviation angle, and this deviation angle, that's what is coming say 13.09. Maybe again we will be putting this as a note, we can put additional deviation as per your requirement. This is basically been done based on computational study. Okay, so we need to be very careful what numbers need to be selected for say corrected deviation. Okay, so this is what will be giving me corrected deviation. Same way, based on this corrected deviation, we need to calculate what will be our corrected camber, and this camber, that's what we are using in our design program for say making of aerofoils. We need to be very careful about this. Now based on that, we need to set our blades, that's what is called say setting angle, or what we say as a stagger angle. So this stagger angle for blade, that's what is coming to be say 8.34 at the mid station. Okay, now so this is what will be giving us idea about how do we do design for the stator. You must be realizing there is nothing more to do for the stator design, because we are assuming our absolute velocity at the entry to be same as exit velocity, exit absolute velocity from the rotor, and what we are expecting at the exit may be axial, or maybe when we are doing multi-stage configuration, it may be possible that we need to enter the flow to the next stage at certain angle. So that's what will be giving me what will be my alpha 4. Okay, so the stator design, that's what we can say we can do simply by understanding in sense with certain assumptions. Now here very important point, that's what we need to discuss is in sense of selection of what we say pressure distribution or what performance we are expecting. Say for 50% span, we were assuming what pressure ratio we are expecting, we are assuming the same number. Similar approach we have done here for say our transonic design, we have assumed our design pressure ratio at 75% of span. Now what we need to do, we need to vary our pressure ratio, expected pressure ratio at different station based on certain assumptions. So for this case, we have assumed our pressure ratio expected near the hub, it is 1.4, and pressure ratio expected near the tip as a 1.66. If we are doing this kind of configuration, what will happen? we will be having say distribution of the pressure, that's what will be varying in a different way. Suppose say if we are varying our pressure ratio to be on higher side from 75% span towards the tip, then it will be very highly loaded near the tip region, and that's what will be subjected to give very high camber angle, and maybe relative velocity also will be coming to be on higher side. This will lead to increased losses. So the meaning is, we need to assume certain amount of say pressure distribution from 75% span towards the tip. Same way from downside of mid span towards the hub also we need to assume our delta P0 in such a way that we will be having uniform distribution of the pressure, or we will be having distribution that's what will be even distribution. If this is not the case, then it may lead to give some kind of zigzag kind of configuration for our blade angle. Okay, now in order to get rid of this difficulty, maybe what we need to do is at 75% span, other than what we are expecting in sense of pressure ratio, suppose say for this compressor expected pressure ratio is 1.63, maybe you can assume say at 75% span this pressure ratio to be on higher side. Okay, and this is what we have done here. So here in this case, if you look at say earlier at 75% span, we have assumed our delta P0 to be slightly same as what we are expecting in sense of design. This is what is been modified here. Okay, so here you can see this is what has been modified. So once you are having your design Excel sheet with you, this is what is the flexibility what you need to keep on eye with. So what we are expecting in sense of pressure rise of 1.63, this is what is the total pressure rise we are expected to be. Okay, and based on modified version with at mid span we have modified our delta P0, this is what is representing the distribution of delta P0. So when we have done design for subsonic compressor, that time also we have discussed the same approach. So in line to that, this is what we are discussing here. Okay, now when we are doing this, we need to keep on eye as we discussed in sense of my delta beta. So this is what is representing my delta beta, that's what is varying from 38 to 11. Okay, same way we are putting our eye for degree of reaction, since this is what is having higher rotational speed and my diameter is also slightly on the higher side near the hub region, and that's the reason why degree of reaction is not a problem. But maybe when we are discussing about the low speed configuration, this is what was a problem. So accordingly we were modifying our delta P0 at the hub. This is what is in a reasonable range, we can say 0.38, and at the tip this is what is coming 0.83. Now diffusion factor also, that's what is now modified. Earlier it was 0.22, and at the mid station this is what was coming as a 0.32, that's what we have assumed. Now based on this, this is what has been modified as a 0.34. We have considered our number of blades to be same, we have considered our chord also to be same, and that's what will be giving us say corrected camber, corrected stagger, and our corrected deviation angle. So this is what is a modification, that's what we have done. So like when we are discussing doing design using fundamental approach, there are infinite number of solutions which are possible. Okay, again as a designer it's you to decide which configuration you will be moving with. Now many times what happens, people they are realizing, if I will be assuming my delta P0 such that you will be setting some trend, and based on that you will be assuming this number. No, it's prefer you just check with how my angles are varying, how my velocity components are varying, and based on that only you assume these numbers. Be careful about this aspect. Okay, so maybe when you are using your Excel sheet on side by, you can keep on eye putting say delta beta is one of the parameter, and that's what will be helping you in sense of understanding what need to be my delta P0. Now, we will not be discussing about the stator design at the hub, we will not be discussing stator design at the tip, because this is what is known to us in sense of my alpha 3, that is what is equal to alpha 2, and alpha 4 we are assuming to be 0. We have done our calculation for number of stator blades, that is what is say 36, and again here in this case incidence angle at the hub we are taking as positive 2 degree. So here we are assuming our incidence angle at the tip, that is what is say minus 2 degree. Okay, and this is what is all calculation at the hub station. Now, based on all this design for say rotor and stator, now the term that is what is coming is to make the blade. Okay, so here if you look at, this is what is representing my rotor blade. Okay, and as we have discussed about the development of DC aerofoil in last week. If you are expert enough to make the program for that, this is what is representing my distribution of the thickness in a circular arc. Okay, and these are the locations what we are discussing at hub, at tip. Okay, and if you look at this leading edge what we are discussing, that's what is slightly rounded, trailing edge also is slightly rounded. So you make your design program at one station, maybe same logic you can apply. Okay, here in this case my whole blade, that's what is also all aerofoils, they are been stacked about CG. So this is what is representing my rotor blade. So you can see this is what is constant tip configuration, this is what is representing in sense of what is happening at the hub. Okay, now once this is what is, you can have your stator geometry, and as we have discussed our stator, that's what is subsonic stator. So we will be using our C4 aerofoil. So here this is what is representing my curvature at hub and tip, and this is also been stacked about CG. As per your requirement you can modify in a later case, maybe you can stack about leading edge, maybe you can stack about say trailing edge. Okay, so this is what is my blade, and this is what is representing my placement of the blade. Now very interesting point here you need to observe for both rotor as well as for stator. What need to be observed? You know, like what all aerofoils we have discussed, that's what program we have discussed. This is what is making 2D aerofoil. That's what is having x and y coordinate, and that too it's in one plane. Okay. Now here in this case, as we have discussed, because of change of my density, because of change of my pressure ratio, my exit dimension will be different. So under that condition, my aerofoil here at the hub station is not 2D aerofoil. Suppose if I say 2D aerofoil, that's what is say I will be having my hub radius to be same. Now based on what is my inclination, I need to modify. So this aerofoil is no more 2D aerofoil, this is what is 3D aerofoil. Okay, so what all cascade data, that's what is available with us, may not work straightway here. Okay, for transonic kind of aerofoil, those data may not work straightway. Now there your computational study that will be helping. Here in this case what will happen, maybe you can have your chord, you need to modify, that is what is one of the way. Okay, based on your inclination you can modify your chord. This is what is say with modified chord, or maybe your expected chord you can change. Okay, this is what is one of the possibility. Later on maybe you need to modify your thickness. Okay, so this is what is very important when we are discussing transonic compressor. For say subsonic compressor, there is no problem, straightway what all cascade data, that's what is available with you, you can use. And that's the reason why most of the time when we are doing our design for transonic stage, we are using or we are making use of computational tools only. Okay, so most of the designers, most of the engine design companies, they are taking help of their own code for doing the simulation, or maybe they are using commercial tools which are available. Okay, now in line to this, here also if you look at for subsonic case also, say the stator is subsonic, say in the case here, in this case here we are having this hub, that's what is inclined hub, this is tip, that's what I say constant tip. So these aerofoils also you need to modify. Okay, so you need to be very careful about selection of these aerofoils and how you will be incorporating these aerofoils when you are making your rotor, when you are making your stator. Okay, so here we will be stopping with, we are interested in doing design for transonic compressor. So very first approach we have selected, that's what is constant tip diameter configuration, and we have done all our calculation at the mid station, we have done calculation at hub station, we have done calculation at the tip station. Based on that, we have changed our aerodynamic loading for fundamental design approach, and we have come up with these blades. So this same design you can try with free vortex concept also, having say constant tip diameter configuration. Now in next lecture we will be discussing about constant hub diameter configuration. That also will be very interesting. Thank you. Thank you very much for your kind consideration. See you again in the next lecture. Thank you.